Hello everyone, this is Applied Statistical Analysis, Week 10. Today we're going to go over regression. Today's lecture is going to be a bit longer than normal. It's because we're going to cover everything that regression can do, from simple regression to multiple regression. This lecture covers multiple weeks worth of material, so you don't have to watch the whole thing all in one sitting. Feel free to break it up into different parts. To review, regression is really cool because it can do both things that we've talked about so far. We've talked about comparing means. We've talked about assessing relationships. Comparing means is all about saying, is one group different than another? While assessing relationships is all about asking the question, are these two variables related? Do they move together? What's awesome is regression can do both at the same time. Again, regression really is the foundation of almost everything we do in stats. Like I mentioned, it can compare group means, assess relationships, and do both at the same time. And it can handle many types of outcomes and predictor data types. Today we're just going to talk about outcomes that are continuous. That's pretty normal. But next lecture, so in a couple weeks, we will actually introduce some other ways we can use regression. As a reminder, regression is all about finding the best fitting line. We have a bunch of data points between x and y, and we're trying to find what line represents this data the best. We're going to do this by minimizing the difference between the points and the line. These are called residuals. Regression is going to do it in a very special way, and the way that it does it is by essentially reducing the space between the points and the line. Remember that the line always goes through where the average of y and the average of x intersect. The line will always do that. And there's two different types of regression. There's simple and multiple. Simple is only one predictor. Multiple is more than one predictor. They're both going to be very similar. When you're in simple regression, when you standardize the variables, it gives the same results as correlation. With multiple regression, it gives something close to what's called a partial correlation. When using a grouping variable, the simple regression is going to give you the same results as a t-test or an ANOVA. And multiple predictors can actually be a combination of categorical and continuous, and you can control for other variables. We're going to talk about that more today. When it comes to linear regression, we're finding the line that best represents the data. And we do that by finding an intercept and a slope. This isn't super different from what you learned in high school, looking at slopes and intercepts of lines. For a simple linear regression, there's only one predictor in the model. We're going to call that x. There's only one outcome. We're going to call that y. So here, the intercept is called, this symbol is a beta. So this is beta 0 and beta 1. Beta 0 is the intercept, and beta 1 is the slope. This last piece is the unexplained stuff in y. So what we're trying to find is, how do we equal y with the information we have in x? So we're going to have an intercept that we're going to find out from the regression. We're going to have a slope that we find out from the regression. And then there's going to be this leftover stuff. We're going to call those residuals. They're the stuff that we can't explain with x. That still is in y. We're going to give some examples to help with this. Before we do that, I want to highlight, using this figure, this one right here, where this line intercepts the y-axis, where x is 0, that is the intercept. So whatever value y is right here, that is the intercept. And the slope is whatever the slope of this line is. So if we move over 1, how high do we go? So it's rise over run, that idea that we learned a long time ago in high school. All right, back to this. An example would be we have two variables, x and y, the predictor and the outcome. We want to know if increases or decreases in x are associated or predict changes in y. That's what I was trying to do. An example of this would be age being the x variable, height being the y variable. If you picture the relationship between those two, age and height are probably going to be related to each other. As age increases, generally height increases up to a point. So if we're looking at a sample of kids aged maybe 3 to 12, age and height are probably going to correlate quite a bit. What regression is going to find is it's going to say, so what is the average increase in height for every year that someone grows up? Do they grow 6 inches on average, 4 inches, 2 inches for every year that they age? Regression would be able to tell us that. This is generally what our data will look like. The y has to be continuous, while the x can be continuous like age, or it could be categorical. Since we've already talked about correlation, it's nice to remind ourselves that regression and correlation are very related. In simple regression, they're basically the same thing. Jamovi provides both standardized and non-standardized results, so we can get both of those with just a few clicks of the button. One thing to note, when we do a regression, we're using what's called a model. Models are just simplifications of the world that help us describe it. So the example that we were using a second ago, where we were talking about age and height, not everyone is going to grow the same for every increase in age, and that's okay. What regression is trying to tell us is what happens on average. So a model is simplifying what is really happening in the world and giving us some information about the relationship between these variables, which often, if we use this right, can give us information that is actionable. A few quotes that I really like about models. All models are wrong, but some models are useful. When you're thinking about what to put in your regression model, what variables, we have to remind ourselves that we're never going to represent the world perfectly. But we want to do it well enough that the results from our regression are useful. And I mean useful when it represents reality and is concise enough to understand and act on it. That's what we're trying to do. This will become more clear as we provide some examples of regression in practice. Before we do that, let's talk about what we need to do regression. The general requirements are we need 2 or more variables. The outcome needs to be continuous, and the others can be continuous or categorical, the predictors. We're going to use the same 6-step approach as we've used over and over again. The assumptions, for the most part, are the same. We're going to add a few. The first 4 are no different than the ones we've talked about before. The individuals in the model need to be independent. We need an interval ratio outcome. The residuals should be normally distributed. We're going to show how we check that with a QQ plot. It needs to be homoscedastic, which means the variance around the line should be roughly equal across the whole line. And then we add these 2 additional ones. This one is we need the relationship between the predictor and the outcome. They should be linear for the continuous predictors. That means they don't curve a lot. In other words, a line represents the data well. You don't need a curved line in order to represent the data. The last one is no omitted variables. This means any variable that is related to both the predictor and the outcome should be included in the regression model. There are some exceptions to this rule, but overall, if there's a variable that is related to our predictor and our outcome, it's good to control for it. This is because regression is trying to tell us how the predictor changes the outcome. But sometimes we can have what's called a spurious relationship. An example of a spurious relationship is researchers found that chocolate consumption was related to crashes, vehicle crashes. As chocolate consumption went up in a place, there were also more crashes. And if you think about this, it actually turns out chocolate consumption goes up during holidays, and driving also goes up on the holidays. So what is actually driving this is that holidays come up and we eat more chocolate, but we're also on the road more, so we're going to be more likely to crash. In this case, it turns out the relationship between chocolate consumption and crashing could totally be explained by this variable that we omitted, which is time of the year. If we included that in our model, the model would show that there's no actual relationship between chocolate consumption and crashes. And that's what we're trying to do with this no omitted variables. We want to control for things that could actually be causing the relationship to happen. This is often called confounding variables. Things that make it look like there's a relationship between our predictor and outcome, but when we control for it, the model realizes, oh, no, those aren't actually related. We'll get to that a lot more when we get into multiple regression today. When it comes to checking these, everything's basically the same. For normality, we're using a QQ plot. Homoscedastic, scatter plots. Linear, we can usually see in scatter plots fairly well. And then the last one, we want to check correlations. We want to know the theory. What variables could we be missing based on theory? That's usually our best option. We want to know, according to theory, what is the relationship here? And that usually guides our model selection, the variables that we actually put in. Sometimes, though, we don't have a whole lot of theory, and so we check correlations. We see what variables are related to both the predictor and the outcome, and we can include both of those, include any of those. Step 2 is, of course, stating the null and research hypotheses. In essence, we're testing if the beta, the slope, is 0 or not. The null hypothesis is saying beta is 0. There's no real relationship. And so if there is any, if beta is not exactly equal to 0, it's just because of random chance. The research hypothesis says X does predict Y. There is a relationship. Step 3, we're always going to be deciding how much evidence is enough to believe the null is not true. We're going to base this on an alpha of 0.05 like we've been doing. And we're going to use the software's p-value to judge if it's below 0.05. We'll ask Jamovi. When we actually run this, we go into Jamovi, we click on regression, and then we click on linear regression. This pane has changed just slightly, but not in any meaningful way, so linear regression will still be right below correlation. When we click on that, it's going to give us this. Our variables are going to start over here, and we're going to bring them over. So the outcome goes here, the continuous predictors go here, and the categorical predictors go here. If you don't have any categorical predictors, you just leave it empty, or if you don't have any continuous variables, you just leave this one empty. What's nice about Jamovi is it gives you clues about what type of variable you're supposed to put there. If it's a ruler, that means it's a continuous variable. If it has this kind of Venn diagram, then it's a categorical one. The results will show up over here. And then there's a bunch of other model options over here. All of these are shown in the tutorial that I have on my website. We're going to talk about what this means in a moment. But overall, the tutorial will actually walk you through that. As I mentioned, the intercept is what y is when x is 0. Sometimes when x is 0 is a meaningful value, sometimes it's not. For example, what's the height of a child when age is 0? It's usually not very important, not right at 0. The age of when they're just above 0 may be important, or not the age, the height of when the age is just above 0. That may be important, but the actual height when they are actually 0 is probably not so much. And that's often the case in a lot of situations. The slope, on the other hand, is a covariation of x and y, how much they move around together, divided by all the variation in y. This is very similar to correlation. It's just how much they move around together based on how much x moves around on its own. What this actually gives us is the slope means it's a change in y for a 1 unit change in x on average. In other words, the change in height for a 1 unit or 1 year increase in x in age. When it comes to the effect size, the beta is one version of an effect size, but so is R squared. R squared is one of the main ones that people talk about. It is the variation in y we can explain over the total variation in y. In other words, it's how much we actually can explain with our predictors. How much do we understand about this variable just based on the predictors that we have? Our example with age and height, it would say how much can we predict someone's height just based on their age alone? The R squared rough cutoff, so it's 0.01, 0.09, and 0.25. And then, as always, you interpret the results and you put it in your own words. Provide an example right here. The example is the regression analysis showed that x significantly predicts y, and then you report the beta. Usually we just put b in the text, so beta equals 0.5, p equals 0.02. And then x accounted for 32% of the variation in y, which means that that's a pretty good amount. It's a large effect. 32%, just to make sure we're okay with that, is 0.32. So it's above large.